podcast is brought to you by LMU Munich.
Thank you very much. It's a pleasure to be here, and I'm grateful for the opportunity to talk, and grateful for the great hospitality that is making us feel so nice and such a pleasant and enjoyable visit to Munich. So the subject of my talk today is glimpses of double field theory geometry. Double field theory is a subject that is really, in fact, as old as string theory because it's based on T-duality. And over the years, there have been several attempts to understand geometrically what this T-duality does for you. And today, I'm going to be talking about some recent developments in this subject in which we begin to see, or we've attempted to see, what kind of geometry could be behind the double field theory. So certainly, there's many things to say and quite a few things to review, but this is going to be the outline of my talk. I'm going to begin by reminding you the basics of this theory, doubling coordinates, some issue called the strong constraint, and some comparison with generalized geometry. Then I'll go and tell you what is the basic action that we use in double field theory. And after that, starting with point 3, I've jumped 4, I'm sorry, there's no missing subject there. I'll talk about Riemann tensor and the geometrization of tensors, some issues with the Riemann tensor as well. And finally, the subject goes into large coordinate transformations in the double geometry. So the material that is essentially new or recent here is all developed in collaboration with Olaf Hohm. And the earlier work to be described here was based on works with Chris Hull, and then with Hohm and Kwak, a student at MIT. So the subject actually has grown quite a bit, and there are many things I cannot talk about. So for example, there's very nice work in applying the double field theory by the Munich group, Andra, Hohm, Larfors, Luz, Patalong. They discuss non-geometrical compactifications, and I will not talk about that here today. There's also quite a bit of work done by the England groups, and Berman, Perry, West, Waldram have discussed interesting extensions and applications of this work to M theory, and I will also not talk about that here. So let me get started. So the basic thing begins with the idea that we have T-dualities, a discrete symmetry in string theory, and associated with the momentum and winding quantum numbers of a closed string, there's the normal coordinates and there's winding coordinates. Those are the conjugate coordinates to winding. They have opposite position of indices and they run over the compact dimensions. So to begin with, there's no doubt that string field theory is a double field theory. So the full field theory of closed strings is in fact almost by definition a double field theory. And the only reason we don't try to understand it directly in the string field theory is because it's still too difficult and there's too many things going on there, so we can't quite see the geometry at that level, at least not yet. So for that, we go back and try to think of the massless sector of the theory. So we consider the low energy effective field theory, two derivative actions, and we ask in what sense is this action duality invariant? What is the remnant of this symmetry for this action? And the answer to that question was in fact given by Meissner and Veneziano a long time ago. The idea is that upon reduction on a torus, you find an unexpected symmetry of the low energy, of the reduced field theory. So you reduce on a torus of dimension TD, assume all fields are independent of the coordinates on the torus, and there you get that symmetry. So the double field theory is the idea that you will double all coordinates. Now this index notation will be used throughout the talk, so please pay a little attention to this. The coordinates that were the xi's and the tilde i's are grouped into a large set of coordinates xm. M is an ODD index. The partial derivatives are grouped as well, and these are ODD vectors. They're rotated by ODD. You also have a very important ingredient here, which is an ODD invariant metric, the metric of the group ODD. It's a constant matrix, it's a non-positive definite, and those are pretty important notation, and we're going to be using that all the time. So once you have this notation, we introduce doubled fields. We double all the coordinates and write a theory like this, integrate over the doubled space. And in this theory, we realize a manifest global ODD symmetry, continuous symmetry, that will give, once you do dimensional reduction, it will give you back this ODD symmetry that was known to exist. Moreover, this double field theory action, when you assume that the fields are independent of the other set of coordinates, will reduce to that action that you have here. Now, there's an important point here, this issue of the strong constraint, that I don't want to belabor too much, but the theory includes a strong constraint. It's an ODD covariant constraint. So it doesn't break the ODD symmetry, but it actually tells you, if you impose this strong constraint, that this double field theory action is at least locally, physically equivalent to the action we started with. In that case, you realize if it's locally equivalent, this double field theory action, in a sense, has truly new information if there's some global issues. But nevertheless, this double field theory action does a remarkable thing of displaying a symmetry you could not display before. So with respect to that strong constraint, there's several views. Let me tell you briefly what it is. It has its basis on a fundamental constraint of closed string theory. This is an off-shell condition. L0 minus L0 bar must be zero in all states. You may remember in a toroidal compactification it gives you this equation. Our fields that are at the massless sector have n equal n bar equal 1, therefore this is 0, and p dot w must be 0. P are derivatives with respect to the usual coordinates, w derivatives with respect to the new winding coordinates, and therefore this off-diagonal product must be 0. You remember the eta metric is off-diagonal, so this constraint can be written in this way with these derivatives we introduced for transparency ago. So this so-called weak constraint must be true for all fields, is unavoidable. I don't think there's any way to avoid this constraint unless you really change how you do closed strings from the very beginning. Fields can still have momentum and winding. Nevertheless, there's a strong version of this constraint, which is a second-order operator. You can demand that products of fields also satisfy this constraint. This is again an ODD covariant constraint, and if true, that produces this truncation of the theory, at least locally, to some frame where the fields are not doubled. So the strongly constrained double field theory displays the ODD symmetry, but it's not locally physically doubled. Now, there's been a lot of discussion about this constraint because ideally, when we first started working on this with Chris Hull, we didn't want this constraint. We wanted to write a theory that had simultaneously all winding modes and all momentum modes, but it's very difficult to complete that construction. So nevertheless, The strong constraint probably is something that could evolve in the near future. We know already that if the strong constraint holds locally and there's a non-trivial global structure to the theory, the double theory may differ from the undoubled one. Moreover, some relaxation of the strong constraint is consistent. In some backgrounds, like massive type 2A theory was produced by Hom and Kwak by relaxing the strong constraint in a tiny, small way, but it was a relaxation. Further relaxations were shown to be possible by Aldazábal, Geis-Bühler in interesting works, and there's an explicit work of Grania and Marquez discussing exactly how much of the strong constraint you truly need in some circumstances. It's an interesting subject, but we will not say more about this now. There's also a usual question, what's the difference between double field theory and generalized geometry? Well, generalized geometry is a small departure from ordinary geometry. In fact, it's a very cautious departure. You have a manifold, and you basically put together vectors and one-forms by adding them as sections of an extended tangent bundle. And then you basically try to define the proper structures on this space. And one of the structures that was defined rather quickly and was the basis of the theory is the so-called Courant bracket, that given a vector and a one form, another vector and another one form, produces a vector and a one form as well. Notice, however, that the vectors and the one forms are not treated symmetrically in this formula. If you have just two vectors, the bracket gives you the Lie bracket. If you just have two one forms, you get 0. So this bracket is very important. Nevertheless, it actually doesn't satisfy a Jacobi identity, and that's quite important in this theory. Double field theory, strongly constrained, I would say, is a small departure from generalized geometry, putting a little more structure. It puts the vectors and the one forms in a similar footing by doubling the underlying manifold. The doubling is never done in the generalized geometry. So this time, we also think of the gauge parameters, for example, the vectors and the one forms. We put them in a single object. It has the one forms here and the vectors. And this bracket gets turned into a more covariant bracket, more ODD covariant bracket, in fact, and we call it the C bracket, and basically takes a rather simple form. It's the Lie bracket plus a correction in which the index, the bracket of two vectors in the double space here, gives you a vector, so you see the index m here. The index m is carried here, and it's carried by the derivative. Now, if the xi's are not doubled, that is, they don't depend on x tilde, this C bracket reduces to the Courant bracket. So, let me say a few words about the double field theory. I must say in advance that my main interest, apart from these applications we've mentioned, has been that I really wanted to understand what is different about Riemannian geometry in string theory as opposed to conventional Riemannian geometry. And you know, this is a modest setup, but we start to see in a very natural way the structures of generalized geometry show up, and I think a few new things are starting to show up as well, and it's a very limited attempt. It doesn't discuss geometry of higher spin fields or any other thing, but just looking at the low energy fields, we're trying to understand what is changing. So one thing that is changing is you can have a nice formulation using the generalized metric shown here. This generalized metric has ODD indices. You can raise the indices with the eta, and it's a constraint matrix so that the thing you obtain by raising its indices is in fact the inverse of the original one. Remember, eta is the constant group matrix. If you have an ODD transformation with HMN, an element of ODD, an ODD rotation, well, it should preserve the metric, that's the definition, and then the generalized metric transforms like a tensor, one H acting on one index, one H acting on the other index. So one of the main results that was obtained some time ago already by Chris Hall, Holm, and myself was the writing of this action in terms of the generalized metric. Each term is ODD covariant, but the combination of them is necessary to find gauge invariance. So the gauge transformations that arise from coordinate transformations generally come from what we call generalized Lie derivatives. If you have a vector, you may recall that the Lie derivative of that vector would have a transport term and this term. The underlying term would not be there. It's funny because it has a derivative with an index up and a parameter with an index down, and this can be done because you have a flat metric. This term is essential for the theory and defines the generalized Lie derivative. Why is it essential? Because trivial gauge parameters, the analog of the fact that the Kalb-Ramond field is invariant under a gauge transformation where the gauge parameter is an exact one form. It doesn't transform. So the same thing should happen here. Gauge transformations are generated by Lie derivatives, and trivial parameters in the double space should generate no Lie derivatives. That's a short computation that uses a strong constraint. Once you have that, these generalized Lie derivatives with hats form an algebra, which is an algebra with a C bracket that I introduced before. The gauge transformations are generalized Lie derivatives, and this duality invariant dilaton is a density. So the action I wrote is gauge invariant because that combination that we showed before, this so-called R, that at this moment is a little complicated, turns out to be a generalized scalar, and therefore the action is gauge invariant. Well, I want to now begin these issues of geometrization, and so the idea was to try to define a generalized Riemann. There was important work done by the Korean group, and then Olaf and myself have been working on this subject. There's some paper to appear very soon explaining some of these things. So we just tried to introduce a Christoffel connection in the usual way through covariant derivatives, and then introduce curvatures and torsions this way, as usually done. The problem is that generalized Lie derivatives or generalized gauge transformations are not the same as ordinary gauge transformations. So while this operation in ordinary geometry guarantees that this is a tensor and this is a tensor, neither one is a generalized tensor. The whole right-hand side is a generalized tensor, but neither piece is. Now, with fiddling with this, and inspired by earlier results of Warren Siegel that worked on this subject in a somewhat different formalism, a framed formalism, we could find, and these people also could find, that this construction in which you take that Riemann tensor, flip the indices, exchange the pairs, and add a bit more of connections is a generalized tensor. So this Riemann tensor seems to be okay, but the purpose of this geometrization was to try to understand a little better whether this is just a trick giving you something very unnatural, or this is a serious thing. So here it goes. Let me talk a little about geometrization of this subject. So we think of vector fields in the tangent space to the doubled manifold, and the connection described, as mathematicians do, as a bilinear operator. Given two vectors, you have this object that is a vector as well, and is roughly the covariant derivative of y along x. This thing is bilinear in both arguments, and moreover, with a function multiplying the vector that is down, you just copies it outside, while a function here acquires an extra piece having to do with the action of the vector on the function. Tensors are multilinear maps from vectors fields to functions with scaling, such that if you put a function here, it should go out. So the way this is beautifully done in mathematics, the golden standard is to define torsion by doing this operation, this covariant derivatives minus the Lie bracket, and it's also a vector, or the torsion tensor, in which you use the inner product to obtain a 3-index object. This is just copied here. The Riemann tensor begins really as a curvature operator that, acting on the vector z, gives you another vector obtained with these commutators, and here the Lie bracket. And the curvature tensor, you take the inner product with w, and now you have 4 inputs, and this is the familiar object we know. So we were wondering if this can be done in double geometry. So for this, you need generalized tensors, and so the Lie bracket is not the right bracket. If you have 2 generalized vectors, this thing is not a generalized vector. So you need a Dorfman bracket. The Lie bracket won't give you a generalized vector. This is a variant of the Courant bracket, and we found then that we could define a generalized torsion by changing the bracket to a Dorfman bracket by adding an extra piece. For the generalized curvature, you would have this formula, and you immediately put this into a Dorfman bracket, and this Dorfman bracket nevertheless doesn't scale properly. It doesn't scale like the Lie bracket, so you need to add extra terms. This is a typical extra term you have to do to fix the scaling of x. When you scale x, there's a problem. So here you fix the scaling of x by adding something that doesn't scale with x, but then you have a problem scaling z, so you have to add more things, and then you complete into a full construction using the geometric objects of the theory, and we're pretty happy about this definition of the Riemann tensor. It has a Bianchi identity like in ordinary geometry, but we find no analog of the differential Bianchi identity. And that seems to be a big puzzle. I will, for lack of time, I think I will skip a little bit of this subject. You have a connection, and ideally you should determine the connection with some constraints, but this turns out to be impossible. You can't fully determine the connection, so in terms of projections using the generalized metric, you have barred indices or unbarred indices according to how you project, and there are some undetermined pieces of the connection, traceless pieces. The non-vanishing curvatures in those projected symbols are these ones, and they all contain undetermined connections. So the generalized Riemann tensor is pretty good, but it contains parts of connections that can't be determined. Nevertheless, when you take sufficient number of traces, you obtain the scalar curvature we found before and the Ricci tensor we found before. There's contracted differential Bianchi identities, but not an uncontracted one. So alpha prime corrections, this subject, due to work of Ashok Sen long time ago, we believe that this ODD symmetry should survive alpha prime corrections, but at this moment we've not been able to understand how to do that, and the lack of a differential Bianchi identity causing some headaches. But we believe that double field theory is the right formalism to classify all T-duality invariant effective actions, so we hope to come back to this problem. Well, the last thing I want to discuss in the last few minutes is large gauge transformations, which was results of a paper published last week. Well, when you have ordinary coordinate transformation of a gauge field, you transform the gauge field with these derivatives. The infinitesimal transformation gives you the Lie derivative. So the question was for us, what is the full transformation that would give us the generalized Lie derivatives that, as you remember, has an extra term? So we wanted something on this style, and there was no guarantee something like that would exist. And to our surprise, something works, and seems to work quite well, and would represent the closest things to diffeomorphisms in the double space. Like everybody that has worked in double field theory has heard the expression, well, don't say it has double diffeomorphisms. It's not quite right. And this goes some ways into clarifying this question. So what we found is that the thing that was just a single partial derivative in double field theory requires this thing with two of them. It's simpler than we thought it could be. Here, the raising and lowering of indices is done with a constant matrix eta. Indeed, if you take a small diffeomorphism, you do find that this gives you the right answer. But that's not enough to find this form. There's some consistency conditions. A partial derivative should transform this way, because it has one index, and should transform this way, because that's what the partial derivative does. And these two things turn out to be the same because of the strong constraint. The constant metric is actually coordinate invariant. That was absolutely necessary and very non-trivial. This F thing is in fact an ODD matrix. And moreover, the usual coordinate transformations and Kalb-Ramond field transformations are reproduced. Another way of thinking of large gauge transformations is through exponentials of Lie derivatives. In fact, if you parameterize coordinate transformations with the parameter xi acting in the exponential like this, you can prove that the usual transformation of a gauge field is that when you think the passive way in which the coordinates are not transformed, you just exponentiate the Lie derivative action. This is a good definition of a large gauge transformation, and we could use it for the generalized theory. And we could ask, well, maybe you should have defined this way the large gauge transformation. So you can ask, does this arise from our definition and some diffeomorphism? And the answer is yes, but not exactly this one, but a slightly different one, in which it's the same to leading order, but acquires corrections at cubic order. And there's a diffeomorphism that makes the exponential of the Lie derivative equal to our form. So generalized Lie derivatives, I remind you, form a Lie algebra. There's a Jacobi identity for the generalized Lie derivatives, despite the fact that the bracket, the C bracket, has doesn't satisfy a Jacobi identity. But the Jacobiator, as it's called, of three parameters is a trivial gauge parameter, so it doesn't matter for the Lie derivatives. So these transformations, defined this way, form a group in which the parameters compose using the C bracket. And as being operators, they're associative, so you really have a group. Nevertheless, the associator of this transformation of parameters is not exactly zero. It differs by a trivial piece that doesn't affect the field transformations. So if you think of coordinate maps, the first transformation being this one, the second being that, the map that is the transformation from x to x double prime is not the composition map. The composition map would use Lie derivatives. The map that works here works with the C bracket, so you have a somewhat more exotic map, this given here. Sigma 1, sigma 2, and the C bracket of these two things. So if you have a third map, actually now from x2 to x3, you can form the map from x to x3 in two ways, and given this extra term over here in the associator, you don't get perfect agreement, and the operations at the level of coordinates don't quite associate. So this is a little exotic at the level of coordinates for sure. The generalized coordinate transformations build the group when acting on fields, but at the level of coordinate maps don't quite form a group. And perhaps this is related to some recent works, many here as well, discussing the possibility of non-associative coordinates in string theory. So it's time to conclude. I think we've seen some hints that there's some nice geometry behind double field theory, and we'll see where that takes us, and we hope that this will find ways make double field theory into a useful language to deal with non-geometric compactifications and learn more about how Riemannian geometry is changed in string theory. Thank you.
Thank you very much. So I think we have time just for one question, please. Yes?
Is there a way to obtain such geometry as a limit of string theory?
Sorry?
Is there a way to obtain such geometry as a limit of string theory?
Well, in a sense, this is all the limit of string theory. It's by the strong constraint, you're guaranteeing that you've truncated really winding or momenta in some frame. So the strong constraint suggests that in any frame that you're working, you really have just momenta or winding. But this is done in an ODD covariant way. So in a sense, this is really string theory, and all of these structures come from string theory. There's nothing non-stringy, I think, about this. I think what would be non-stringy is to keep just the massless sector and include all the winding modes and all the momentum modes, but not all the rest of the massive modes. Then you would be doing something different from string theory. But at this level, I believe this is all string theory, and the idea that you must double the geometry is really there in the full string theory from the beginning.